Atomizer. My friend here loaned me his. Which way is advancing? Very good. So by way of introduction, it's no surprise to all of you that there is an increasing need of both waste management and energy. So let's marry that partnership. Let's bring those together as an opportunity to use human or animal waste to generate electricity. So I've got this little diagram: eat, excrete, and heat. And if you didn't like that, people, pellets, and power. So my work is to directly spray concentrated sludge into energy harvesting equipment. So a lot of my work is adding controls in CFD to maintain consistent droplets in spite of a large varying in the properties of biosludges. But today we're going to be focused on the atomization itself and the properties therein. So primary atomization is a complex topic. I'll give you just enough to be dangerous, assuming that you don't know more than I do already about it. So anytime two fluids meet at different velocities, you're going to have an inviscid mechanism of instability called Kelvin impulse. And when you bring in different densities, you've got Rayleigh-Taylor instabilities. And when you bring in surface tension, you've got Rayleigh-Plateau instabilities. Given enough time, these instabilities working together, they're eventually going to disintegrate the liquid into droplets. Viscosity and surface tension, they're your enemies. They're going to restrain that. You all in here know atomization, you know that. Now, I spend a lot of time working in CFD and validating and confirming my methods, but that's not the focus of today. So you guys did a great job of governing equations. I'm not going to provide that. In short, though, I'm using an explicit linear interface reconstruction, VOF technique, which is numerically stiff, SST turbulence model, which is wrong but useful, Fluent, which is also wrong but useful, and very small time steps of approximately E-8 seconds. What I found was a lot of surprises, a lot of problems, data processing, a lot of runtime. I run about 100,000 time steps per wave you're going to see in this atomizer. 1 out of 10 do not recommend. So our atomizer is a twin fluid with steam as the assisting flow, moving along the center with biosludge around the outside. We have steady, unswirled feeds, but inherently there is going to be unsteadiness and swirling result in this. I will not be discussing that much today. We have a cold non-Newtonian biosludge with a Hershey-Bulkley model where there's beyond a yield stress, the material will flow, and then during that flowing, as the shear increases, the viscosity decreases. So the steam shear, the velocity difference, is what creates those primary instabilities that are going to generate breakup. But the steam also heats the biosludge and lowers that viscosity curve. So we have an additional benefit to produce viscosity to aid in that. So here's just a snippet of our atomizer and a bit of an instantaneous snapshot. Flows from left to right, where there's a wave of the biosludge being formed. As that biosludge lifts up into the channel, here's the center line there shown. As it lifts up in the channel, there's a high blockage ratio. So this produces a repeating wave system at high velocity. I call it wave augmented varicose explosions. And I've talked a lot about this in various papers. Here's a video from CFD, flows from left to right. I've got two sets of contours superimposed. The backdrop is contours of Mach number, where light colors are high, blue are low. In the foreground is contours of pressure on the surface of the interface, where dark is high and light colors are low. And you see in general, the wave is two-dimensional because of Kelvin impulse at first, and then there's, of course, azimuthal variation as the wave develops and collapses. A few other animations. On the left-hand side is Mach number, where light colors are high and dark colors are low. You see this repeating compression, expansion. And on the right is outside looking in at the interface of the surface as it's blasting and spreading radially out. So where are we headed with this? This is a base case. It does actually fairly well for viscous fluid atomization, but I've never optimized it. That's our very little secret there. It's been studied extensively. My first paper in atomization sprays in 21, a few in physics of fluids, a couple more recently, and then my most recent in a brand new journal, Transport Phenomena, that describes how spontaneous swirling occurs in this atomizer, even though you haven't planned on it. But no other permutations have been tried. So we think about the menu of options to try to optimize this. Of course, the first two things you think of are flow rates and geometry changes. Well, we've got a few geometry elements to work with. We've got our beach, our pool, various things that occur, but I'm going to pick off the menu. I'm going to pick nozzle diameter, okay, with some small fries. I'm going to be working on this today. So this should be easy, right? Every time we do a geometric modification, it's going to require reblocking, remeshing, interpolating from prior data, then restarting that CFD model. The meshes are 100% hex. They're not cut cell. They're, part of the adaptation is, but the base mesh is not cut cell. So it's time consuming to block and remesh. And then on top of that, the slow workflow, oh, here's the mesh, sorry, this is a 90-degree cut. 2.1 million cells just for 90 degrees of it. And there's the different view of the inlet, steam inlet, everything is hex. But anyway, even though this process is long, every time we start it, there's always surprises. Boundary condition transitions, there are settings that we may not transfer, bugs because ANSYS has them and shares them with me frequently, thank you ANSYS, and divergence every time we start one of these models up. Even though we're interpolating from a prior flow field, there's problems, there's always problems. So what is plan B if we don't want to manipulate the geometry constantly and restart CFD models? Well, we could have a moving deforming mesh. Here is a two-dimensional view. Instead of having a fixed orifice diameter, we could have a moving flap. I started this type of work back in '07 with moving agglomerating mesh. And so that's an idea, but what happens when we move in 3D? Because this is just two-dimensional. Well, I hate TETs, and ANSYS requires unstructured mesh to be doing this in 3D, and I'm not going to do that. And also, when you're talking about a three-dimensional object with a reducing orifice size, you're talking about now a fan of things collapsing. I definitely do not want to do that in CFD. So what's plan C? Plan B was a failure, plan C. Research question is, can we fake the system? Can we fake a wall with porous media to augment this process? So here's a cross-cut of a mesh, flows from left to right, three-dimensional with this 2D slice, 3.3 million cells for this 90-degree model. And this is the region where I've got a porous media implanted. And I'm going to be considering that as my base case orifice size. So the idea of this is I can use a three-dimensional user-defined function to tune this on the fly, both the resistance level and the location of this. And that location can be moved axially and radially with a simple user-defined function. Simple, relatively simple. So we've got this idea of using a porous media, and again, this will be replacing that wall, part of that wall. So sidebar, how do we treat porous media? Well, it's the Ergen equation, right? So the pressure drop is a function of a viscous term and an inertial term. Here are the constants. We're going to focus on alpha, which is permeability, which is the first part of the viscous term. You'll recognize the inertial component, 1/2 rho v squared. Everything is 1/2 rho v squared. But we're going to, again, focus on that. So what we found, first thing I did was a two-dimensional axisymmetric proof of concept, all right? 2D axisymmetric is very bad for droplets. There's no such thing as droplets in 2D because they're toruses. Well, droplets along the center line can be droplets, but droplets outside of the center line will be a torus. And so, but it's okay for the wave, it's not okay for droplets. So I'm just studying this for the wave. So here's some animations. Here's our base case on the left, the porous media on the right with the porous media zone there blocked off and shown just for your interest. So what we see is the same basic behavior between the wave formation on the left and the wave formation on the right. So we seemingly have success. We like this. And a presentation was given yesterday, 62259, about how we use video analysis and measurements on the screen to determine if it was accurate or not. So the issue is, what resistance level do we need to fake the wall? Okay, so I did some early optimization work to realize I need something on the order of 10 to the 8th reciprocal meters squared to make it seem like a wall. So now what I'm plotting here is orifice open area versus resistance. And what I mean by this is I had to toy with it to figure out what resistance and what size of that little ledge I needed to produce the same steam differential pressure. Okay, that's what controls the droplet size, the steam differential pressure. So I found that as I start increasing the resistance, I have to open that nozzle up or lower that ledge more and more to get the same steam differential pressure. So that is not what I was looking forward to, but at least at my lowest viscous resistance level, that's only about a 4% change in nozzle open area, so it's fairly close. Yeah, anyway, so as I said, it's going to increase that. Now, if we look at the steam pressure, so steam is pulsing, and I'm looking at the temporal coefficient of variation. This is normalized by the base case value versus resistance to that porous media ledge. So what I see is at first, lowest porous media setting, it's actually increased the steam pulsations. As I increase the resistance, it decreases the steam pulsations. And here's the magic number. If I use 10 to the 9th resistance, it actually matches the steam pulsation 1.0 of the base case. If I want to look at the frequency of that steam pulsing, it is affected by the viscous resistance, frequency versus resistance. When I first engage the porous media at the lowest setting, 10 to the 8th, I get a slight reduction in the forcing frequency, the natural occurring frequency, not forcing frequency, and then that, of course, saturates out to higher values. So what does it look like in 3D? This is 2D proof of concept in 3D. I'm going to show you 3 animations. These are the same Mach number contours you saw earlier, where this is the wall for the orifice. The next is a 10 to the 8th porous media, and the next one is a 10 to the 9th porous media. So we've got 3 animations all looking at the slices on the center line. What we see is the same basic functionality among the base case, the low resistance, and the relatively high resistance case. But what's interesting though is this intact length of the slurry annular region is longer for the wall than it is for the highest porous media resistance. So the annular region doesn't survive as long, which is going to have implications on droplet size, as we'll see in a minute. Similarly, we've got 3 animations outside looking in where the slurry interface is colored by its dynamic viscosity, where high values are lighter colors, low values are darker colors. We see a similar behavior, but as you saw in the previous slide, the intact slurry annular dimension has been reduced by using porous media. So you look, the annulus survives less and droplets are produced sooner. Lastly, temperature, because the steam is pulsing, expanding, collapsing, you get compressive heating and cooling. We see a similar relation among the different permutations, but the temperature penetration region is a little bit farther down in this one than you see on the far right. I've moved that red arrow a little bit down and captured the interface of the yellow. It's hard to see in here, you have to watch the individual videos and it's tedious, but we do see a different penetration rate. So now I'm going to be discussing droplet size. This is a busy diagram, droplet size versus time. What we do is we collect 10 bins of droplet size, 10 equal volume bins moving from along the atomization trajectory right at the orifice down to where we're no longer measuring. And where my time scale is convective time, which is 1 over the wave frequency. So I'm showing you effectively the number of wave times. Here I'm only showing you the last 100 wave times, all the time it took me to run this model to get it quasi-steady state. I've thrown that data away, and this is clearly quasi-steady. These statistics are no longer changing with time. So as we look at the time average, this is time average solver mean diameter versus distance from the nozzle. Distance has been normalized by orifice diameter, so we're looking up to about 3 orifice diameters. We see the base case is about 2,000 falling, trending downward. The porous media 1/8 to 8, the lowest porous media case, kind of is already dropping down, and higher porous media resistance is even lower. So we see that as we start to increase porous media, we start to reduce the droplet size. And our research question was, can we do this without affecting the flow field? So we are not completely unaffecting the flow field. How those droplet sizes vary in time, the temporal coefficient of variation of droplet size versus distance. See that the lowest porous media setting is comparable with the base case, but then as we start to increase that porous media resistance, we start to get a reduction in droplet size variation, which is good. You want smaller droplets and you want more uniform droplets, but we did not want to affect the geometry or affect the flow physics with our porous media. Last data set I'll show you, this is pulsing frequency of the droplet sizes, because they're pulsing as well. They're moving with the steam. We see for the base case a primary function of naturally occurring frequency of about 1,000 hertz. And then with porous media, we saw a drop in that natural level of fluctuation, and then with the higher porous media setting, we see a slight increase. This effect is greater in 3D than it was in 2D. I know this is small for the room, but I'm showing the 2D version of this. And you see maybe a 9% reduction in recurring frequency with the first porous media setting, and here it's more like a 20%, so it's exaggerated in 3D. So I've gone as fast as I could to try to get through everything. Snooze fest is over. Congratulations, you're at the end. So porous media can be used to manipulate geometry effectively in CFD with some limits, right? So higher porous media resistances tend to homogenize the droplets, lower the pulsing amplitudes, lower that frequency, then raise the frequency depending on your level of porous media. But that is reducing the intact fuel length, which is going to have some negative impacts. The higher resistances also force us to open up the nozzle more for the effective opening diameter, which conflates the data. We were hoping not to see that effect, but we did. Effects are stronger in 3D than they are in 2D. And I probably would like to go back and revisit when earlier I mentioned that 10 to the 8th is the minimum resistance that would have like a wall. I'd like to go back and revisit that and see if I can get lower, because my goal was not to affect the results. And clearly we are affecting the results by adding porous media. Acknowledgements. Thank you, Wayne, which is me, for your support. And Elijah Yoder, my PhD student, I forgot to put him in the proceedings. He made all the meshes for me. So thank you.
Any questions? Exactly 15 minutes. We have 15 minutes for questions.
Yes, Gabriel.
Why do you put the data in terms of, or why do you make the Why do you non-dimensionalize the data and results? So for example, when you're going length, you put it in terms of the diameter.
So that it's more universally applicable, so other people might be able to repeat the research, and because that would apply to nozzles that are on the centimeters here or meters somewhere else for a given Reynolds number, Mach number, whatever.
Thank you.
Compared to, yeah.
Great. Thank you for very nice work. I have questions. For me, it's not clear. It's possible you explain about your model to break up on the bubble, the droplet. Sorry, you have to
Yeah, so there's no model.
use some model?
No, there's no model for breakup. This is just a balance of forces. So momentum versus surface tension. And we're resolving the interface as others have done before me, using VOF, using a linear interfacial reconstruction. I don't know what the second one, I don't know if OpenFoam has Plick in it. OpenFoam has Plick? Okay, good. I wasn't sure where OpenFoam was with that. But yeah, we're using Plick. But yeah, there's no submodel. It's just producing droplets explicitly.
Okay, when you break up some, or form some droplet, you explain about what's the methodology to remesh the grid?
Yeah, so the
Or
mesh, yeah, we're not remeshing. I found in some other work I published that ANSYS automated mesh refinement is bad for business, so don't use it. So we don't use automatic remeshing, but the mesh is small enough to capture the droplet. So we're trying to get 4 or 5 mesh elements across a given droplet. You know, this thing is far, if you look at the animations, there's nothing spherical about these results. So, yeah. So you want to call those droplets, but there are droplets, they're not spherical, but there's no need to remesh because we're resolving the droplet.
Okay.
That's why this takes months on hundreds of cores to run. So, yes.
Have you also considered to use VOV to DPM maybe?
Yeah, I have. I've got a paper on that. I just sent a copy to Rizwan via email where I've done that for flow focusing and flow blurring, but I haven't done that on this yet.
Because we were also doing similar case, but we found out that so I'm using normally oak tree because then you can like reduce those.
I don't like to cut cells of octree, but I know.
Yeah, me neither, but yeah. But yeah, we figure out that for these VOV to DPM, oak tree shouldn't be used because I don't know, it just cuts. The lipid doesn't spread like normally. I don't know. Do you have similar? I don't know. Do you have similar experience or not?
Yeah, I do. That's okay. That's octree is kind of like ANSYS is automatic mesh refinement. Yeah, and that's a problem for Plick, for the piecewise linear.
Okay, so I'm gonna have to
Yes.
interrupt. Thank you so much, everyone.